most of us live our lives by without ever questioning the force that seems to bind us all together, gravity. In this video, I'll try to change your perspective on how gravity really works, or even if such a thing exists. But by the end of this video, you will realize that it might be better to think of the ground accelerating upwards at 9.8 meters per second squared, and that this object experiences no forces on it. Part 1. Problems with Newtonian gravity. Newtonian gravity explains that two objects fall to the ground at the exact same time because their inertial masses and gravitational masses exactly equal each other by coincidence. We're not going to settle for that argument. Newtonian gravity explains that light travels in a straight path with a constant velocity without being affected by an object's gravitational well. However, this is not true because we know that gravitational lensing exists, and we will talk about that really soon. Newtonian gravity incorrectly assumed that space and time are absolute throughout the universe, regardless of your frame of reference. Newton predicted that Mercury's orbit around the Sun is something like this. However, it has been experimentally found that Mercury's orbit around the Sun is something like this. Part 2. Superiority of Einsteinian gravity. First of all, Einstein would argue that gravity is not a force at all. You see, the backward jolt that you feel when your car accelerates forward is no different than the force we call gravity. He called this the equivalence principle. Consider you're in a closed box out in intergalactic space where there are no forces influencing you. Now, say that the box starts accelerating upwards at 9.8 meters per second squared. What you would see is that the ground is coming up towards you, but more substantively, the two objects would hit the ground at the exact same time. If you were dropped from a cliff on Earth inside the same box with the exact same lab setup, you wouldn't be able to tell whether you're on Earth or out in intergalactic space. Therefore, the equivalence principle implies that freely falling frames of references and stationary frames of references are both the same and that they're both inertial. Now, if you consider gravity to be a force, then light shouldn't bend around any massive object. Yet, it does. And here is why. Consider you're inside a closed box, which is accelerating upwards, and a beam of light passes from one end of the box to the other. If your frame of reference is directly aligned with the beam of light, you would see that it travels a straight path and the box accelerates upward. However, if you were inside the box, you would see that the light bends downwards in a parabolic motion. So what you can infer from this picture is that if you were to track the path of a photon of light inside a closed box as you accelerated upwards really fast, you would see that the photon is traveling a roughly parabolic path. In fact, exactly parabolic path. And this is basically what happens in gravitational lensing. From this picture, you can see that light from a star behind our sun bends around and reaches us. So, if light travels in a straight path with a constant velocity, why does it bend? Good question. This brings us to part 3. Curvature in 4-dimensional spacetime. Try saying that 10 times. So remember how in part 1 I talked about time dilation and length contraction? Well, in our 4-dimensional spacetime, whenever an object travels, length contraction and time dilation in essence balance each other out. Now suppose you're inside a rocket that's traveling really fast out into intergalactic space, and you have this apple along with you. Now suppose an observer is looking at you while you eat the apple. Viewed from Earth, the size of the apple would appear to have contracted. However, the time it took you to finish the apple would appear to have dilated. Therefore, when viewed from different frames of references, certain amount of space seems to have exchanged for a certain amount of time. Therefore, Space-time is any mathematical model that combines space and time into one single interwoven continuum. Now, to relate time dilation and length contraction, you can take the time dilation equation and solve it for the velocity, plug the velocity value into length contraction, you get a big messy equation, simplify that down, and you end up with the nice and elegant equation. So the equation that we just derived, in a way, combines time dilation and length contraction into one single equation, signifying that space and time could be considered as one single entity. So why 4 dimensions? Well, consider this. Space consists of 3 dimensions, x, y, and z, and time consists of 1 dimension, which you can only go in one direction, that is forward. I think we're now ready to talk about curvature in 4-dimensional spacetime. So why does space have to be curved? Well, here's why. Consider the sun in the center, and we have our planet Earth here, and this is a star. We have talked about this earlier, that light from this star would have to bend around the sun to reach us. And this seems to be in seeming violation of the fact that light travels in a straight path at a constant velocity. Why is this not straight? Well, you can tell it's not straight, and it's not constant velocity because at every point, the slope of the tangent line to the curve is changing. Hence, this does not seem to be like constant velocity. Here's where curvature kicks in. This picture depicts that space-time is being bent around massive objects. And what you can see here is that light is really traveling a straight path from the star to our planet, but the space-time is being curved, so light is traveling a path that appears to be curved, but in reality, in terms of space-time, light is really traveling a straight line from the star to our planet. The path that light takes in a curved space-time actually has a name for it. It's called a geodesic, and a geodesic basically denotes the shortest distance possible from point A to point B in a curved space-time. Now let me demonstrate what curvature is with these pieces of papers. So essentially, if you parallel transported a tangent vector from a point around a curve back to the same point, and if you get the same tangent vector, space-time is flat. And if you parallel transported a tangent vector around a curve back to the same point, and if you did not receive the same tangent vector, that is, the angle was different, space-time is curved. So in conclusion, the more deflected your angle is, the more bent space-time is. We're now finally ready for the best part of this video, that is mathematics of curvature in 4-dimensional spacetime. We're going to focus on what's called the Einstein field equations, and more importantly, what's called the metric tensor. What's a tensor? A tensor is essentially a combination of two vectors, which together yields a value of 0 regardless of your frame of reference. Now let's consider a situation where we have a box and a force is being applied at an angle and the box displaces a certain direction in the right. And you realize that work equals force times distance. However, we are concerned with force times cosine of this angle because we really want this component of the force vector. Now consider that the force is being applied from the top instead from the left, and you realize the angle that it makes from the x is 90 degrees. The work done equals 0. These are the Einstein field equations. These are tensors, and essentially you plug in the amount of energy into the stress energy momentum tensor, and this tells the left hand side or spacetime how to curve, and curved spacetime tells mass how to move. Your change in height as you move in x1 direction is given by equation 1, and your change in height in x2 direction is given by equation 2. If you move in some random direction s, your change in height is given by the sum of the x1 and x2, is essentially this equation. This can be generalized into the summation term, where m is your dimension going from 1, 2, 3, 4, etc. Here the Pythagorean theorem works in a simple way. ds squared equals dx1 squared plus dx2 squared. And this can be summarized using this summation. Let's multiply this by what's called a Kronecker Delta, where if m equals n, then this value is 1. And when m does not equal n, this value is 0. Let's use this equation and plug in dxm in place of d phi and dxn in place of d phi. Plug in the values in place of the original equation. And essentially, this term is the metric tensor. This equation that we just derived allows you to find Pythagoras in curved spacetime, and this equation allows you to find Pythagoras in Euclidean flat spacetime.